Without further ado, we move to a different topic, which is our last topic of this course. It's very short because we don't have enough time, but also because it's an easy topic, at least from the conceptual viewpoint. Playing with the code might be, if we would do a lab, that would not be a short lab because the code of OSPF, for example, is very large, but it's a very easy topic. So it's called link state routing. And this is illustrating a database. This is just illustrating a table, because the idea of link state routing is that all routers that perform link state routing have a topology database that describes the entire network. Mm-hmm. Okay, I've lost the return channel here. Okay, so it's the day today. So link state routing is primarily a method that has been developed for IP routing, and it's known, and the most widespread method is OSPF. It's used in some large provider IP networks. Today it's also used for bridging. We have seen that the principle of bridging is that it should be transparent, and it builds a tree using the spanning tree protocol by eliminating some ports or some links so that there is no loop in the topology. That's what is done by the bridge that you can buy from Migros, for example. If you have more sophisticated bridges, which you should not have because bridging is in principle only for very small local area networks, but the sad reality is that you have lots of places where you want to build very, very large bridge network. In that case, you do what is the equivalent of a routing protocol, and this is typically done using link state routing. So the most popular solutions are Trill, which is a Cisco thing that has become an IETF standard, and shortest path bridging, which is the competitor of Trill, pushed by other companies and by IEEE. So they're all based on the same principle. So the principle is brute force. Don't try to be smart like in the distance vector. Distance vector is smart. We have this distributed Bellman-Ford algorithm that converges to the correct solution even when there are changes and wrong initial condition, which is entirely non-obvious. Here there is nothing smart. You just do the brute force. So each router keeps a complete map of the entire network. It's the GPS solution if you want. If you want to go somewhere, you have a GPS that has a map of all the worlds. It computes a path from where you are to where you want to go, and then it shows you where you are on this path and how to go. It's almost the same here, except of course you don't keep the same GPS with packets. Packets will move from router to router and will still need to read the routing table, but the idea is the same. Each router keeps a topology database of the whole network. Routers compute their routing tables based on their topology database. And of course, to keep the topology database up to date, you have an updating mechanism, which is based on flooding. Whenever there's a change in the local topology, which occurs, for example, when a link dies, when the link dies, all the routers that were connected to the link will inform their routers of the suppression of that link, or when a new link is added, or when a new prefix comes. Let me skip that. Those are the kind of details we'll look if we do at the lab. So let's look at an example. Here's an example with 6 routers. How would the system work? Well, through flooding, so initially, each of the routers knows what are the interfaces that it's connected to. That's part of the configuration. You might have automatic configuration. In the lab, we had to configure. This is bootstrapping the routes. For example, C knows it's connected to N1, N4, and N5, and has to give costs, for example, which can be derived from physical properties of the connection. Then all routers will inform the neighbors. For example, C will inform B, D, A, and F of the connections it has. For A and F, it's no new information. They're already connected to N1. But B, for example, will know that C is connected to N1, to to prefix N1. So B will know this, and then B will inform also all of its neighbors. In that case, it's only A, and it's not very exciting because A had the information already. But D will inform, for example, E, that C is connected to N1. It is, if you want, is the same principle as Bellman-Ford, except it's in the algebra of concatenation instead of adding. A router learns from the neighbors. With Bellman-Ford, it learns the distance to a destination, and it repeats that to other neighbors who add their own cost to find the distance. Here, instead of adding the cost, we concatenate. A router learns of all the neighbors and what they're connected to, and then it gives that to their own neighbor, which then adds to their own list of who is connected to what. They add what they have obtained. And at the end, everybody will learn everything. Of course, that might create loops. For example, F might repeat to C the information that it has heard from he who had heard it from D, that C is connected to N1. It will, but of course there will be, first C will notice that this is not new information, and there is a numbering mechanism in the messages. So the messages are simply flooded. There is no processing of the messages. When C sends an update about the fact that it's connected to N1, this message is simply repeated to E and to F and back to C. But there is an ID in the message. So if a message is looping, you remember that you saw this message already and you delete it. So this method is not memory cheap, right? You need a lot of space in the routers for doing that. So solutions like OSPF are meant for routers that are ready to spend a lot of memory or disk space to contain all this information. This is why also when we can do redistribution of BGP into OSPF, because the routing protocols that employ this technology are designed from the beginning with the capability to handle very large routing information. Then, when all routers have received all information, I say when, but of course everything is asynchronous. When a router decides that it has enough information, it will do a shortest path computation. And for the shortest path, you need a graph. So this is the graph, for example, that any of the routers in this network will build. I say any because all routers will have exactly the same topology database if there is no failure or mistake. So every router will build this graph. In the graph, we take the convention that if there is a local area network like N1, a network prefix that is shared medium, which is the general case, we add it as a node to the graph, and we put a cost of going to that node equal to the true cost we gave to the network, and in the reverse direction, we put a cost of 0. So this is, for example, how A, C, and F will know that they're connected to N1. We do that because in a graph, you have only binary relationship between nodes, whereas here, we would need ternary relationship because A, C, and F are all connected to the same. So you build this graph, and then you perform a best path computation. Now, OSPF usually wants to compute shortest path. You give a metric to all links, and you want to compute shortest path. So what is the best algorithm for computing shortest path? Best in terms of complexity is Dijkstra's algorithm. So with OSPF, you run Dijkstra's algorithm. Why do we use Dijkstra with OSPF and not with distance vector? What's the reason? Yes?
Because distance vector needs to run distributedly, it's also working distributed.
Exactly, because Dijkstra, we don't know yet how to make a version of Dijkstra that would be distributed and would not have the same complexity as distributed Bellman-Ford. So Bellman-Ford is not the algorithm you should use if you compute the shortest path in a centralized way. You should use Dijkstra. But if you want to distribute it, Dijkstra is not appropriate for that. And we will understand why in a minute here. So every router has the global topology. It will compute the shortest path from itself to all possible nodes. So it will compute a shortest path tree rooted at self. How does Dijkstra, this I can skip. How does Dijkstra work? Well, here is Dijkstra's algorithm. It's one of the beautiful algorithms, like Bellman-Ford, but beautiful from another viewpoint. It's beautiful because it's quite mysterious why it works. It's not mysterious. There are proofs of why it works, but it's intuitively not so obvious. So Dijkstra works by adding nodes to the tree one at a time. And whenever a node is added, it will not move. It's exactly on the tree where it will be. So it's a greedy algorithm, if you want. Whereas if you compare to Bellman-Ford, with Bellman-Ford at iteration k, we have a given distance, which is the distance in k hops. At iteration k plus 1, the distance will change. And the next hop, the routing decision I have at step k, might be changed at step k plus 1. As we have better and better information, we change the routing information. In Dijkstra, it's not the case. We add the nodes one by one. When they are added, their place on the tree will not change. The algorithm works in the following way. So I am at node 0, and I want to find the shortest path for all nodes. So I have a tree that I'm building, which is M, and at every step, I compute the pair of nodes that minimize. So M of I is the distance from me to node I. I try to add at every iteration a pair of nodes where one of the nodes is already in the tree that I've built so far, and J is one that is not in the tree. So I'm trying to add some nodes, but for that I consider all the existing nodes that are already in the tree, and over all those pairs I find the one that has the smallest distance from me to J. That one I add to the tree. So the one that I have, I add it to the tree, and the path to that J0 will be via the I0, which is already on the tree. This is how it works. So let's do the example of this node here. I am zooming on node A. So initially, node A has only itself with a distance of 0. Then at the first step, it looks at all the neighbors, all the nodes, all the pairs that are inside and outside. So inside there's only A. So the first step of the algorithm consists in find the neighbor that is the shortest, that is the closest to me. Here it's C, so I add C. So the pair I0, J0 is AC. I add C, the distance, and I add the label of C, its distance is 10. And I add this link, the predecessor of C is A, so I add this red link to the tree. This is the state of the tree at this iteration. Next iteration, which node will be added to the tree? I'm not sure this one works, but I've lost my control panel, so I don't know whether it works or not. So we will see. Doesn't work? Okay, good. So let's do it manually, which always works if everybody has hands. So who votes for 1? Node F will be added. Wow. Who votes for 2? Node E. Who votes for 3? Node D. Who votes for B? Okay, so Dirac on F, which is of course the correct solution. So node F will be added. And then if we continue, node E will be added, then node D, and eventually node B. So as I said, the miraculous thing is that when we add, for example, node E, we know that the shortest path will be there, and at the end of the algorithm, it will not change. So at every step, we don't know where to route completely, but for all the things we know, they will not change. The downside of it, or the counterpart of it, is that in order to know if the problem was how to go to B, we know it only here at the end of the algorithm. So it's not an incremental algorithm like Bellman-Ford has that property that it's not a greedy algorithm in the sense that what is done now may be undone later. But if you don't run the algorithm until the end, you have an approximation which is not bad of what you will get at the end. You have a route in k hops instead of k plus 1, at most k hops instead of at most k plus 1. But you have something which is an approximation. Here with Dijkstra, you don't. Until you've run the algorithm completely, you have no clue where to route to B, for example. You get that only at the end. That is the property of Dijkstra. So in this route, in this network, all nodes will apply this formula and will get, for example, the shortest path. And then it's a bit like in model predictive control. The only thing you keep of the shortest path will be the next hop. So you do a complete computation of the complete tree, and the only thing you keep is the next hop that you put in the routing table. So for example, A, we know in order to go to B, we go via N2, and for C, we go via N1. And in order to go to D, for example, the next step will be via C here. But so A has this complete tree, but it's not used for routing. When a packet goes from A to D, for example, A will use the information. It has to go via N1. And then when it reaches N1, it will need to know what is the next hop. The next hop will be F, probably here. And then it will, at F, it will use the routing table of F. It will not use the information of the tree that was available at A. Though all nodes have the same topology database, they have different shortest path trees. For example, if I zoom on C, here is the shortest path tree for C. So the topology database is the same, but of course every node does its own shortest path computation, which will lead to different results. And the routing table at C, of course, will be different. What happens when there are changes to the topologies? Then there are, like in BGP, changes are sent to neighbors. And whenever the new information is received, you need to recompute the entire tree. I said Dijkstra is a bit like a waterfall approach. You know the routes only at the end, but there are incremental computations from Dijkstra. So if you change one link in a graph, there are ways that are a little more economical to recompute the shortest path than to redo the entire computation. But in principle, any change triggers recomputation of the database here. I mentioned that link state routing is used in routing. Per se, so in the classical sense of routing, so for IP routing in the internet. It's used also for, as I mentioned, bridging. So here's an example. Assume you have a very large bridge network, like we have in fact at EPFL. Assume you have lots of virtual LANs, and you want, because you believe in virtual LANs, which most companies do, you want to interconnect them by bridging. For example, you would like that all the machines here, here, and here, all the red virtual LAN machines are bridged across the EPFL infrastructure, which means if somebody sends a packet from here to here, it should be as if they would be in the same local area network. So you need machines here that are treated as bridges. We have seen that one way to do it is the spanning tree. And if we apply the spanning tree without any subtlety, we will need all the R boxes to be spanning tree bridges and to build a blue and a red spanning tree. There's an alternative to this, which can use link state routing, which I would like you to imagine. Could you vote electronically? Doesn't look, I have only 11 connections. So let's use the manual approach. One says, so of course you need a bit of stretch of imagination. So those are routers. So they have their own routing stuff. But they want to use, to make bridging. So of course they will use tunnels. They will put the MAC layer packet in IP packets that will go across this interface. If we use the link state approach, that would mean that they have their own routing protocol, but they use the link state approach for this bridging function. This is what is meant here. So who thinks one is a solution, is a good solution? Who likes solution one? Okay. Oh, I don't. Who likes solution two? Not very popular. Who doesn't like any of the solution? Okay, so none of those solutions are liked. Let's see what is the industry solution. 24. So you are right if you didn't like any, but perhaps you should talk to Cisco because they propose one. So solution one is what is used in one of the solutions I mentioned. So two doesn't help because if you just propagate the MAC addresses of this guy, you propagate this to all of the routers. So what is the problem? You would like that a router like R7 knows that in R5 there is somebody that belongs to the red virtual LAN. So in order to know this, it has to know not just the MAC addresses, but also the fact that the label of the VLAN that is used here. So just forwarding the MAC addresses would not be sufficient here, unless you do a spanning tree per VLAN. One is doable. So what is done if you have VLANs? Then all routers talk to all routers using a link state routing protocol, where they propagate not a topology database like we did in the case of IP routing, but a map of the network, which is the map I drew here, saying whether there is somebody of a given VLAN in a given router. So the map that is drawn here, R5 has somebody of the red VLAN, and we pass this information everywhere, and then a router like R5 knows all that stuff. It knows that there is R1, R7, that there's a R1, R7 and itself that has red, and the others not. So having done this, each router can compute the shortest path tree to create the spanning tree of this VLAN here. So R5 will do it, for example, using the red tree, and so all routers will do the red and the blue tree here. And then all MAC layer packets will be forwarded inside tunnels, MAC in IP tunnels. So routers like the one in the middle just do normal IP routing. Right? They don't need to do more. So if we want to summarize, this is very simple. All nodes compute their best path, but it's brute force. Of course, the memory requirement, the space requirement is large, also the computing requirement, and the code is also very large. But this is made for networks where you think you will have lots of information. Now, what is the main difference with distance vector? The main difference is the definition of the cost can be very flexible. In distance vector, we need costs that are essentially distances. The only flexibility we have is which distance we give, which cost we give to a link. If we have a centralized view with a complete topology database, we can do lots of more interesting stuff. For example, we can use application-specific routing, we can, for example, decide that some type of traffic may need to use links that will not use, for example, satellite links. Satellite links have a latency of hundreds of milliseconds. If you want to do interactive audio on it, you would like to avoid them. So in the topology database, you can give information. This link is a link with a very large latency. When I compute a shortest path route, I may, for example, exclude those links. So I may compute one shortest path for low latency traffic, another one for other traffic here. And other things. I can do also what is called quality of service routing. I can use paths that have enough bandwidth available for some type of traffic and for some other types. So we can do lots of fancy things here. It gives much more flexibility. Now, if we talk flexibility, we start going on the overlapping with another way to do flexibility, which we have very briefly alluded to. We didn't do a lab because the lab's already large enough, as you have complained. It's called, we have found another way to do things like I just mentioned. Route voice traffic a different way than the standard way. What is the other way to do this? Well, today it's called software-defined networking. You can have a direct access into the router that will supersede the routing decisions that you normally do by using flow routing flow tables. This is typically used in bridge network and data centers, but some operators think of using it, for example, in their large operator network. Of course, link state routing is, in some sense, providing the same solution. So we will see what of these things will converge. Link state routing, like distance vector routing, is a fully distributed solution, contrary to software-defined networking. Software-defined networking is a centralized solution where the only distributed thing is that we have the capability to talk directly into every router, but we need a centralized computer to do the job. What is best? We don't know. Centralized solutions have lots of drawbacks. They're centralized, they need a centralized computers. Distributed solutions are more flexible, you can deploy them more easily. But centralized solutions also give you an easier control. It's easier to understand what happens if you have a central SCADA or a central big screen in which you see all the decisions that you've taken, instead of configuring 200 routers and hope that those local configurations will converge to what you would like to do. That could be the end, but since we have 10 more minutes, I will use them. When people say OSPF, OSPF is Open Shortest Path First. So as I mentioned, is one of the routing protocols for big single domain networks. OSPF uses link state, but not only. OSPF uses also something a bit like BGP. It uses some form of hierarchy inside a domain using a very interesting thing that we will see now. So hierarchical routing means if I have a network that is very large, I would like to split it into sub-networks, but they're all inside the same domain. So one way to do it is to use BGP, and it's a valid way to do it. So, and some operators do that. They have, as we have seen with BGP, you can have confederations, for example. You can have part of a domain that have private AS numbers, and that's a way to separate the domain. But typically BGP is not used when you want fine-grained traffic engineering. You want really to compute the amount of flow that goes everywhere. You don't use BGP, but interior routing protocols. OSPF is one of those. OSPF uses the same hierarchical principle as is used in BGP, but that's the beauty of it. Of course, things are different. So this will give us an opportunity to see how you can how you can organize in a different way a two-level hierarchy of routing. With BGP, things are hierarchical in the sense that there is BGP and interior routing protocol, but with BGP, the hierarchy is by having nodes that are BGP routers, both at the interface between two subdomains. So when you have two autonomous domains, you have one BGP router at each of the sides of the interface between the two. In OSPF, it's a bit different. In OSPF, you have different subdomains, and the routers that serve as boundary between the two belong to both domains. So X3, for example, is a border. It's called boundary router between this area. So the subdomains are called area in OSPF, between area 0 and area 2. So it has to belong to both. In BGP, we don't do that because typically BGP is for different organizations. If Swisscom and Sunrise peer, they don't want to have a router in common. They can have a link in common, but not a router in common. OSPF is meant to be within the same domain, so it makes sense to have a router in common. Second, OSPF makes the assumption that the topology itself is hierarchical, which means that there is a backbone area and periphery area. Backbone area is called area 0. The peripheral areas are called numbers other than 0. And it's a strict hierarchy in the sense that all traffic from area 1 to area 2 must go via area 0. It's not possible to connect area 1 and area 2 directly. If they are connected, it must be to area 0. Then the principle is, inside an area, we use link state routing inside an area, and between areas we use distance vector. The simplest is to see an example here. So here I'm showing those areas with three routers, D1, D2, D3. So what is D1? D1, I guess, is this one. So this is showing which are the top. Oh, okay, no, should not. Okay, A1. Sorry, we are at A1, router A1. So the principle is, within an area, we use link state routing. Across areas, between areas, we use distance vector, which means that a router like X5 that belongs to those two areas will inject in another area the distances to all the prefixes it has learned, but only the distances. Now the question is, I am at A1 and I'm proposing three different views of the topology database that is available at A1. Which one is the correct answer? So let's do the manual solution. Who speaks for answer 1? Thank you. Who speaks for answer 2? Thank you. Answer 3? A bit more. Who doesn't know? Well, here is the solution, and I guess the best is to go through all details to understand. So this is the topology database at a given, at any router in the area. Remember, the principle of link state routing is the topology database is the same. So at any router at A1, but also at X5, for example, the topology database has the view of the link and all the connected networks. Now we see that we have also N1 and N2 that are connected. N1 and N2 are in fact here. So how did they come to be visible here? Well, first, inside area 2, each of the 4 routers have this topology database, which I quickly summarize. Of course, there's more information. There's the value of the links, but it shows this, N1 and N2. Then a router like X6 or X4, for example, inside area 0 knows the topology database, which is the networks that are inside the area, plus X4. Because it belongs to area 2, it computes its shortest path to N1. So what is the distance from X4 to N1? It's 10 plus 1 if we give a distance of 1 to the directly attached link, so it's a distance of 1. So X4 is at the distance of 1 of N1, and of N2 at a distance of 17. So X4 does as if it will inject in the topology database the information. I have a link, I have N1 and N2 that are connected to me, but with a distance 11 and 17. This is a distance vector principle. You don't give more information about N1 and N2 than the distance from you to that. So they inject this. X6 does the same thing, but the distances are different. The distance to N2 should be 11, that's correct here, and 17. So X6 will put this in the topology database here. And this topology database with the link state update mechanism is propagated everywhere. So all 6 routers in this area have the same vision here. Now, X5 will now do the same thing, which belongs to both area 0 and area 1. We'll do the same thing in area 1. So X5 now in area 1. X5 in area 1 will compute its distance to N1, for example, and will find a distance of 29. It uses the total topology, and it will find a distance of 29, for example, and 23 for N2, and similar for that was for X3 and X5. So this will then be propagated to the entire area. So A1 will know that it is this information, so its own cost to N1 and N2 will be computed using those values plus the internal cost here. So that means that the correct answer was answer number 2, which was a small majority. Voila, that's all that we will see today about distance vector and link state routing, and for today and for this year. So see you tomorrow for the last test of the year.